Welcome to this video lecture on statistical power. In this video I'll cover a few topics including what is statistical power, what factors control the power of an experiment or analysis, what kind of things do you use it for, and at the end I'll tell you why you should never calculate statistical power based on the observed data or results that you get. So let's jump in. First, to understand how statistical power works, it's useful to briefly recap the process of statistical significance testing. So imagine we have some population with a true but unknown to us mean and standard deviation. So let's say we're doing a statistical test to compare the mean of that population, or a sample that comes from that population, from another group. So the null hypothesis here would be that the two groups come from populations with the same mean. So that means that our second group, if the null hypothesis is true, should have the same mean value. But the group that we're getting is actually a small sample from the population. So its mean won't be exactly equal to the true mean of the population. So maybe if we draw a data set, 100 individuals or 100 observations from this population, maybe we'll get a mean that looks like this blue circle here. But imagine we take another random sample of another 100 observations from the population. Maybe the mean of those 100 will be this. And we do it again, get another sample, randomly drawn from this population. And so let's do this many, many times. And we might end up with something that looks like this. This is a distribution of sample means, and it's called a sampling distribution. So this thing called a sampling distribution, it's what we'd expect to find if we obtained many samples from the true population with a particular sample size. So the conventional cutoff for statistical significance, alpha, this value called alpha, traditionally set at 0.05, is related to this sampling distribution. So we can find the area under this curve that represents the most extreme 5% of our randomly drawn means, which we do in both directions. So that means that 2.5% of the means in our sampling distribution, if we made 1,000 random samples, each of 100 things from our population, 2.5% of them would fall within this tail, large in this dashed line, and 2.5% would be in the other tail. So we call every outcome outside of these dashed lines statistically significant, and outcomes inside of them not significant. So let's shift to statistical power. And imagine that we're comparing a second population that actually does have a different mean than the first population. So they truly are different. But our second sample is actually also drawn randomly from that larger second population. So that means that there's going to be a sampling distribution of the sample means. So the blue is sort of the distribution of means we might expect from our first population, and the orange is the distribution of means you might expect from our second population. Sometimes the sample mean will be larger than the true population mean, sometimes it'll be smaller. So if the sample mean happens to fall below the threshold for statistical significance, the dashed line here, we would not reject the null hypothesis. But in this case, this conclusion would be incorrect. I told you that this sample does in fact have a different mean. So this is what's called a type 2 error. It really should be recognized as significant, but we failed to recognize it as significant. But there's also going to be a range of outcomes here where the sample mean is greater than the threshold for statistical significance. So the area under this part of the curve represents the probability of correctly identifying the outcome as significant. And that is what is statistical power. It's essentially the area under the sampling distribution. It's the probability of correctly identifying an outcome as significant. So what controls statistical power? Well, for one, if the true difference between populations is smaller, such as in this example, our power to recognize that difference will be lower. Conversely, if the true difference between the populations is larger, the power to recognize that difference will be higher. Similarly, the true variability of the populations also matters. When the true population has low variability, statistical power will be higher because our random samples are going to be more likely to be closer to that true mean. But if the population is more variable, there's greater variance in our populations, The distribution of sample means from that population will also be more variable, and it'll be harder to recognize this difference, so we'll have lower power. So this combination of population mean and population variability is called effect size. And this is a key thing for statistical power. A large true effect size, some combination of greater difference between means and or smaller variability of the populations will yield higher statistical power. And conversely, you'll have low power if you're searching for something that truly is a small effect. So effect size is referring to the characteristics of the populations, but your sampling decisions also influence the power that you're going to have. So for one, if your sample size is small, it's easier for the sample mean that you get to differ more from the true population mean. Imagine you have a population and you only take 3 observations from it. The chance of your mean of those 3 being close to the population mean is not that great. So as the result, the sampling distribution is wider and the power is lower. Conversely, if your sample sizes are large, the sample means that you get are more likely to be close to the population mean, and the power will be higher. So finally, you can also increase or decrease power by changing the significance level alpha. You can either make the test more strict, which would decrease power, or you can make it less strict, which would increase power, but with the trade-off of increasing the risk of a false positive. But in practice, we don't change the significance level alpha. It's conventionally kept at 0.05. So these 4 parameters, effect size, which is a function of the true population difference and the true population variance or variability, sample size, power, and significance level are all related to each other. So you can calculate any one of them by knowing or specifying the others. But in reality, we don't change the significance level. So there really are only 3 parameters to use. So what are you going to do then with these parameters and with statistical power? Well, one very common and useful approach is to specify an effect size and a power, and then calculate the sample size that would be necessary to recognize that effect. And so I'll come back later on to talk about what is sufficient power. I'll also come back to how you would determine the effect size, but for now, note this is the effect size that you expect in the population. So you're expecting a particular effect size, and you want to have a certain power to recognize that. What sample size do you need? You could also take a known sample size that you have and ask, what is the smallest effect size that I could detect with a given power? Say you want to know, for my sample size, what can I detect with a power of 0.8 or 0.5? For example, maybe you can only detect fairly large effects given your sample size and power, which means that it's difficult to rule out there being a small effect, for example. And finally, you could ask, what is the power of this study given the expected effect size and the sample size, either anticipated or actual? Here you might wonder, if I have a particular sample size and the effect size is some value, what would my power be? Is the power going to be reasonable, or is it going to be too low? So you can see how you can take these 2 things and calculate a third in a variety of ways to get at different ideas. Okay, so back to the question of what is sufficient power. Power values are going to range between 0 and 1 because they're a probability. 0 means that the entire sampling distribution is less than the significance threshold, and therefore there's no chance of recognizing a truly significant result. A power of 1 means that you should always be able to recognize a significant result. And as with many things in statistics, there isn't an objective definition. There's no firm cutoff for what is good or sufficient power, but a power of 0.8 is sort of widely used as a convention for good. If you have a power of 0.8, then that's widely thought to be good, pretty good power. But really, this is a decision for you to make where you draw that line. And really, if your power is 0.799, that doesn't necessarily lead you to different conclusions than if your power is 0.801. So these are always sort of subjective decisions that you need to make based on your own judgment. But there are real dangers in studies with low power. Say of a power of 0.4 or 0.2 or even less than that. And here's the real danger. So when the power is low, any statistically significant results you find are going to be misleading. So imagine this situation here with a small true effect between the blue and the orange curves, but also very low power. So to be identified as statistically significant, any result, if you get a result that has a p-value of less than 0.05, you might conclude that there is a significant difference. But to become statistically significant, the observed effect that is required must be much larger than the true effect here. So statistically significant results are going to have exaggerated and larger effect sizes than in reality when the power is low. They might be 2 times, 3 times, or even 5 to 10 times as large as the real effect. But even worse, there's also a chance that some of the statistically significant results that you get in a low-powered test might actually be in completely the opposite direction of the true effect. There are situations where you might get a result that is statistically significant, p-value of less than 0.05, but it's actually in completely the wrong direction if you have very low power. So very low power or underpowered tests are very problematic, and so that's why it's important to sort of consider power and sample size and effect size and all these things. So back to effect sizes. How are they estimated? Well, the effect size is a property of the population. It isn't based on your samples or your data, so you must estimate it from your knowledge of the subject. You must think about what you know about this system, what's previously known, how this effect might compare to other effects that are known, and so forth. And so, in most cases, we're using power to evaluate scenarios. How many samples would I need? Could I detect this effect? And so forth. So effect size is basically an educated guess, an educated estimate based on theory, prior expectations, and so forth. So we've talked about effect size. The examples that I've used here have been in the context of 2 samples. But it can be measured in other ways as well. So with 2 samples, it's called Cohen's d. It's just the difference in means divided by the standard deviation. But there's more ways you can get effect size. You can do it for ANOVAs. You can get effect sizes for parametric correlation, where it's just the correlation coefficient R. You can get effect sizes for linear models, either single regression or multiple regression models. You can get effect sizes for chi-squared tests. So in all these situations, what counts as a large effect or a small effect will be different in different subject areas. Different scientific fields, different fields will have different sort of effect sizes. You should think about what makes sense in your subject area based on what you know about the topic, based on theory about the topic, prior work, and so forth. Remember, effect size is not based on your data, it's based on your sort of expectations about the situation. So that's very important, and here's sort of my final thing. Effect sizes are based on the population. Do not calculate the effect size from your observed data. Well, why not? Well, for one, the post-hoc, which means after the fact, so the post-hoc or the observed power from the effect size that you observed is just directly related to the p-value. So the graph on the right just shows a simulation of many random experiments showing how if you know the p-value, the power is exactly the same thing. It's not telling you anything useful here. And more importantly, the observed effect size that you get is often a noisy estimate. In theory, if you did multiple, random draws from the population, the mean effect size would hopefully approximate the mean of the population, but you only have one effect size in your data, and so therefore there's going to be some noise. And so in reality, post hoc or observed power does not reliably indicate the true power of the test. So I now have 2 curves on the right here. One is based on a true power of 0.25, and one is based on a true power actually of 0. I just simulated drawing from the same population twice. Well, it's hard to tell which one is which. The upper one has a power of 0, and the lower one has a power of 0.25 true powers. The curves are the same. It's possible to get either high or low observed power that's completely unrelated to the true power. So remember that power calculations require you to specify an effect size based on what you would expect in the population. It doesn't matter that this is an estimate, that you're sort of making an educated guess here. You can never know the true population, but power analysis is used to evaluate scenarios and to help guide decisions, like how many samples do you need, or to help you interpret results. Could you have recognized a particular effect? So it's very useful to do power evaluation either before or after running a test to help guide what you can say about your results and what they might mean.